All right, for our last bit of time today, I want to hint at applications of improper integrals to probability and statistics in particular. And this is going to come up in a homework problem. Let's start by looking at the homework problem, actually. Then I'm going to assign for Monday. It's this problem, number 53. It's an application. It says that the probability that a light bulb manufactured by a company lasts at least 100 hours is given by this integral. That's a pretty strange thing to say or to do, but is actually a very common thing to do, to represent probabilities, likelihoods by integrals. What are probabilities? First of all, they are assessments of the chances of something happening. When you say there's a 90% chance, the CEO claims 90% of the company's light bulbs last at least 1,000 hours. That means the probability is at least 0.9. Interpret the 90% as a decimal without a percent sign, you'd write 0.9. To do this problem, you're trying to say, is this statement accurate? You need to do this integral, this improper integral, when A is 1,000. It's not super hard to do, actually. Oh, thank you. I didn't notice that. I didn't notice that with the first class. I'll have to send them a message. 100 hours, so 1,000 hours would be 10 hours, 1,000. So A would be 10, yeah. Do the integral when A is 10 and see if you get an answer of 0.9 or more. If you do, then the CEO is right. 90% last 1,000 hours more, meaning 1,000 hours or more. If you don't, then the CEO is wrong. You're supposed to do the integral. But anyway, the main point is it's an application of an improper integral. The function being integrating has a name in this situation. It's called a probability density function. Probability density function. And this kind of probability density function is very common in exponential decay. Got an example like this in Mathematica. This function is exponential decay. 1/10 e to the negative x over 10. The capital E there represents the number e. Don't use a lowercase e. Plot it. Yeah, that's exponential decay. What does it mean to be a probability density function? One thing it means is that integrating the probability density function gives you probabilities. So for example, I might wonder if X represents the lifetime of a light bulb, what are the chances that X is between 0 and 10? Integrate the probability density function to find out. In exact form, it's going to involve E. What is it in approximate form? It's about 0.63, about a 63.2% chance that the light bulb is going to last between 0 and 10. It's the area under the graph, right? Because it's an integral. If I integrate in from 10 to 20 instead, you can see the area under the graph from 10 to 20 is smaller. I'm going to get a smaller answer. That's a smaller probability of lasting between 10 and 20. Altogether, your light bulb is going to die at some point. there's 100% chance that the lifetime is going to be between 0 and infinity. The integral from 0 to infinity has to equal 1, which represents 100%. Probability density functions have to be greater than or equal to 0 in their outputs, and they have to integrate to 1. And oftentimes the integral is an improper integral, like this one, with an infinity. Other kinds of improper integrals are important as well. Another kind of improper integral in this situation that's important is one that will compute what's called the theoretical average or theoretical mean lifetime of the light bulbs. But before we do that, let me illustrate how you can do some simulation in this situation. I'm not going to require you to know this code here, but I'm just showing it to you anyway. This code will create what's called a probability distribution. Seems like it didn't really do anything, but now if I do this code with random variate and this D here that is the same as the D there, this will generate 100 simulated data points from this distribution. There they are. What I want you to notice about them is that most of these numbers are fairly small, less than 10. However, every once in a while, you get a pretty big number, relatively speaking, in the 30s, for example. There's a few of these that are in the 30s. There's one at least in the 40s right there. Every once in a while, you get a big number, an outlier. If you've had statistics, you know about outliers. If I plot these data along with the probability density function in the same picture, what do I see? I see that the data are more dense where the probability density function has a higher value. That's not a coincidence. That's why we call it a probability density function. This is analogous to some physics situations that we're going to study in chapter 8, where we might have like a thin wire made out of, I don't know, tin or something. And that thin wire could be more dense in certain spots than others. The molecules could be more tightly packed. And if that's the case, if it's not a uniform density, we can model it with a density function that is not constant. It goes up and down, perhaps. And where that function is higher, the molecules are packed tighter together, it's denser. And where it's lower, the molecules are a little bit more spread apart. You may not be able to macroscopically tell where it's more dense and less dense. You could experimentally verify it's denser in certain spots than others. This is analogous to that, except with data instead of wires. The data are more dense where the PDF probability density function is higher and less dense where it's lower, though every once in a while you've got an outlier. In statistics, it is important to compute averages. Officially, they're called means. What's the mean of the data here? These data. What's their average? Add them up and divide by 100 in this case, you're going to get close to 10, it turns out, I predict. Somewhat close to 10. Not exactly. If I do it again, I get a different simulation. I get a different average. Still relatively close to 10. I'm trying to get it even closer to 10. If I do 1,000 data points instead of 100, yeah, there's 1,000 data points. Yeah, now the mean is closer to 10 for sure. Of course, if I make the plot, it'll be too many points. Yeah, it's really dense over here, though you can't really tell. I'm going to go back to 100 data points. That means closer to 10. This integral, this improper integral, here's my final point for today, where I take x times the PDF, x times the probability density function. This improper integral from 0 to infinity gives you the theoretical mean. And it's exactly 10. Exactly. The simulated data has an arithmetic average close to 10. The probability density function that is modeling the data has a mean of exactly 10. Hinting at some things in advanced statistics here, but it's a kind of advanced statistics that's super useful. People who do advanced statistics on the job are doing this kind of stuff all the time. I'm not talking really basic statistics, I'm talking more advanced. But they're thinking about these distributions, probability density functions, means, simulations, even integrals all the time. Okay? We'll get into this in the most depth that we can at the end of chapter 8, which will be probably after spring break. But I wanted to hint at it here right now as motivation for improper integrals. All right, see you on Monday.